So thanks again, everyone, for joining us for the EarthEngine at SG event. So now we are beginning with the parallel talks. And for our session, we have Mong Suan. So Dr. Mong Suan is a co-founder of Kumi Analytics. She led and grew the engineering team at COSS.io. She previously founded a software development company, Insight Software Pte. Limited, Malaysia, that was then acquired by Cardsis. Insight Software provides product development and consultancy firm for wireless and software projects. She was the CTO of Sweet Spot, a proximity-based marketing platform company, and BeLoyalty, a loyalty platform company. Prior to this, she has worked as a research scientist, development engineer, and team leader in wireless research laboratories, semiconductor companies, and consultancy firms in Europe, including Toshiba Research Laboratory, Qualcomm, Motorola, TTP-Com, Aeroflex, Sarquans, and Cambridge Consultants. She has been involved in IEEE 802.11n standardization and wireless chipset development for GSM, UMTS, and LTE. She has participated in LTE eNode B system testing and validation in Europe, USA, and China during LTE rollout. She is a prolific inventor with numerous patents, and she is a co-author of a wireless communication book and authored over 200 IEEE publications. Mong Suan graduated in electronics from the University of Southampton with first-class honors in 1995 and received her PhD from there with a thesis titled Neural Network-Based Multi-Level Equalization Techniques. Thank you so much, Dr. Mong Suan for joining us today, and she will be discussing machine learning in Google Earth Engine. So we'll provide a bit of instructions to our participants regarding the Q&A, and I give the floor to Dr. Mong Suan. Thank you very much.
Thank you, Cheryl, for the introduction. Just a little, just to confirm, today's session is machine learning in Google Earth Engine for this session. Sorry, I'm trying to change the slide. Okay, about Kumi Analytics. Kumi Analytics is headquartered in Singapore. We have a US subsidiary. Among our leadership team, we have around 75 years of remote sensing and neural network experience. Our company is dedicated to help financial service company to benefit through the use of location-based technology. We have industry partnership with Bloomberg, Google, GeoWorks, Metric Spectrum, and Battlefield. Machine learning has been used in GIS for spatial analysis. It's formed part of geo-processing tool for classification, prediction, and clustering. Here for this example, machine learning in Google Earth Engine is used to predict the crop production. Here we will first do the crop identification. The crop mentioned is corn and soya. Here we have corn in yellow and soya in green. From the crop identification, we can calculate the area or the planted acreage estimation. Note that for crop identification, we have crops which is multi-seasonal in an area. So different crop could be planted and harvested at different time. So we have to set a window, different window for the classifications. So there's quite a lot of problems that we have to solve to estimate the agriculture production. Machine learning for Google Earth Engine is also used to estimate the forest carbon sequestration. For carbon sequestration, we estimate the above and below ground biomass. Here in this example, we actually predict the above ground biomass for year 2017 and 2019. We can see the above ground biomass has increased due to the reforestation activities. We need this to monitor quite a few forest reforestation activities that involve in green financing activities. Machine learning is also used to help in property valuation. Here, in this case, we use object identification to identify a few property attributes. We have attributes such as swimming pool, roof area, solar panels, trees, grass. And from that, we're able to calculate the area of these attributes as well. I have here a list of various machine learning model in Google EarthEngine. We have the supervised classification model. We have the clustering, or also known as unsupervised classification model, and prediction model. So for supervised classification, we need to determine which category an object should be assigned to. For example, whether area is the sea area or is a land area, for example. And for clustering, we group observation based on similarities in values or location. For prediction, we try to estimate the value of attributes, such as trying to estimate the above ground biomass that we mentioned just now. In the classifier package, we have a few, In the classifier package, we have a few classifiers such as CART. So CART is a classification and regression decision tree. We have the random forest. So random forest is a combination of a few CART to provide a better classification performance. We have also the gradient tree boost, where we, instead of doing the classification, the random forest or the CART in the decision tree in parallel, we do it sequentially to sort of help a weaker decision. All these are based on decision tree classifier. We have also the naive Bayesian, which is a Bayes classifier. Here we assume the training data is Gaussian distribution. Another classifier is which is very popular, is for vector machine. We have to the maximum entropy classifier, which is also based on probabilistic classifier. Finally, we have TensorFlow. The good thing about Google EarthEngine is that is an integration on the AI machine in the Google Cloud. So there's I will show you later how they are integrated. Here we have for TensorFlow, because of the integration, we can have a convolutional neural network, machine learning, and also deep learning. For the cluster package, we have the k-mean clustering. So k-mean clustering is a model-based clustering where all the k distribution is assumed to be Gaussian with equal variance. We have the covariate clustering, where the clustering is hierarchical in the form of a classification tree. We have also the learning vector quantization clusterer. For the prediction model, we have linear regression. This is based on the reducer package. So I will show you a little bit on the reducer package later on. So in the linear regression, we have a normal ordinary linear regression. We have the robust linear regression where the regression is done iteratively. And also the rich regression where it's based on L2 norm, L2 regularization. For the prediction, we can also use the classifier package mentioned above by setting the output mode as regression. And again, we can also use the TensorFlow package for the prediction model. Here, I show you some of the workflow of the machine learning in Google EarthEngine. We take example of land cover classification. The first thing we need to do is define a model. And you can see in line 34, where we use a random forest classifier. Here, 10 means that we are using 10 trees for the classification. For the training, as you see on line 28, we actually use a random sampling to get 5,000 pixel as the sampling for the training data. So the training data will be a land cover type from the MODIS dataset. After training, as you can see from line 42, we are able to classify the input imagery. From the classifier package, we also can derive the confusion matrix. So from confusion matrix, we can try to we can get the training accuracy. So on your right side, we can see the training overall accuracy is around 95%. And below that, we have the error matrix. Like the vertical part is actually the real values, and the horizontal part is the classified values. So we normally train with a set of training data, and it could overfit. So it's quite a common classification problem. So here we actually obtain, try to get validation data, as you can see from line 49 onwards. So again, we take 5,000 pixel as validation data samples, and we classify again using the same trait classifier. You can see the validation accuracy drop to 67%. So it's quite important that we choose various classifier and try to get to make sure that the classifier is generalized, meaning that it can work for the training data and also work with data that is not used for the training. For the assessment, just like I mentioned, we can get find out about how good is the model through the accuracy function. Here is the accuracy will provide the overall accuracy. We can make use of kappa function as well. Kappa coefficient measures the agreement between the classification and the truth value. So 1 is for perfect agreement and 0 for no agreement at all. Just as I mentioned, the training data is derived from random sampling, meaning that we take an area, we randomly select training samples. We can also select pixel by pixel using Google EarthEngine pixel selection as training data. We can also, here for this example, we can choose a region here, which is in black in the image on your right. So we choose a region where there's forest, and also region where there's no forest. So we can use this function called image sample region, which we have to define the area and the scale of the sampling pixel. So for example, if you want a sampling pixel to be 5 meter by 5 meter, we have to put a scale of 5 meter and so on. So for this region, every pixel in the region will be the training point. We can also select sampling. Sorry. So the code below is just an example how the training sample is obtained and used. So we have to define the polygon, we have to define the class of the training data. So we again, I mentioned just now, we can also use stratified sampling. So for stratified sampling is sometimes we don't really want to get totally random samples. We want it to be based on class. So for this example, we want to get 800 data points, and we have 2 classes, 0 and 1, could be forest and non-forest. Here, for this example, we want to get 400 samples from non-forest and 4 samples from forest. But if the area of the non-forest is larger, we can choose to have to increase 400 to 600, for example. So stratified sampling means we actually can control how many samples based on the class of the data. Okay, now back to the different training methods of the different model. Just now I mentioned we have the classifier model, we have the clusterer model, and we have the reducer model. So for the classifier model, we need to define the band that is going to be used, the band of the images that is going to be used for training, and also the class. So for example, this is land cover type 2. And this will fit into the properties of a feature. And we have a list of features, and all these lists of features is defined for a feature collection. I assume that you have some basic knowledge of Google EarthEngine at this point. So for the clusterer, we define the same thing, but without the class, as we do not require any knowledge of class for clustering model. For the reducer, we normally for linear regression, we have to define the x and y values. So x will be the dependent variables, and x will be the independent variables, and y will be the dependent variables. So for this case, we try to estimate the maximum temperature or precipitation. So we have to define the time and an arbitrary constant value, for example, as the input values. So this 0 and 1, then it will be the x value, and 2 and 3 will be the y values. So from all this, we will be used as going to be used as input for the reducer model. So this could be bands for image collections or image or properties in the feature collection. What I mean here is the input to the model can be either image collection, image, or feature collection. Okay, for classification, there's actually quite a lot of problems for classification and prediction. There's quite a lot of issue that we have to solve. It's not it seems very simple just now as I showed. It's just a few lines. We just define the classifier, we define the training, we define we just process start the classification or the prediction process. There's but for the real is non-ideal. So normally we don't have a full coverage. So we normally have a non-regular coverage over a region for the satellite imagery. So some of the satellite images could be missing due to clouds and shadowing, and also when the satellite is scanning the Earth, some parts could be missing because that's real life. So what we can do is we have to pre-process the missing pixels. For example, for this example is cloud and cloud shadow. So one of the example is using self-organizing coordinate map. So I just provide a reference here for example. But there's quite a lot of pre-processing method that we can use to sort of fill in the missing pixels. So we can, for this case, we try to understand what is surrounding the missing pixel, and we all for certain images we could have images for different days. So from all this information, we can actually give an estimate of the value of the pixel. We can also use auxiliary data. For example, let's say if you're using Landsat data, for example, we are using Sentinel dataset, and some part of the Sentinel dataset is missing. So Sentinel is 10 by 10 meter, is higher resolution of Landsat, but we have no choice. So because it's missing, so might as well just use some sort of information. For this case, we can use the Landsat data set. So another problem we face in machine learning is overfitting. We could, just now as I mentioned, or as you can see, the training procedure is able to provide more than 90% accuracy from the training data. But once you verify it, it's not really generalized. The accuracy from the validation data dropped to around 60%. So for this case, there's a overfitting scenario. So the model is fitting too much to the training data and is not able to generalize. So for this case, we have to use cross-validation technique. So cross-validation technique is we use different set of training data. Let's say you have 1,000 training data, you probably use 900 for training and 100 for validation. And we choose another set from the 1,000 data, and we train again. So we try to train a few times and also validate a few times from the same set of 1,000 data set. So from that, for each training, we try to train different classifier. So just how you could see there's you have quite a lot of classifier or models. We have random forest. We have gradient boosting, random forest classifier. So or support vector machine. So we try a few different models and try to find which one generalize better to avoid the overfitting. There's also problems of class noise, which means that there's errors and mislabeling present in the training data. Sometimes the class are even missing. So for example, let's say an area can be classified as forest area, but it's actually a river. So this mislabeling. This will impact the accuracy of classification. So some of the suggestions include like maybe we pre-process the training data as well. So we could remove or mask out any data that is actually a river. There's a few data set which in Google EarthEngine, which can provide you the area where there's river or waterways, for example. So this can be used to try to pre-process the training data set. There's a lot more, but I will not go too much into it. So in summary, Google EarthEngine is able to provide robust tools for machine learning models. There's a few range as you see just now, and you have clusterer, you have classifier, you have regression. It has a very extensive sample data for analysis. So we have Sentinel, we have Landsat, MODIS, and we have data set like for example, a USDA data set for crops and precipitation and so on. So do check it out. We are also able to add our own data set. For example, high resolution satellite imagery, which is not available for free. So you can actually add your own data set into Google Earth Engine. We also able to perform batch processing and able to automate easily using, for example, JavaScript, Python script. Do check it out if you haven't sort of look into Python scripting for Google Earth Engine. And the machine learning is scalable through Google Cloud Platform. We are able to also integrate with TensorFlow engine with Google Earth Engine. So it does support industrial grade processing of data. Do check out our TensorFlow engine integration via Google AI platform. So currently, Kumi Analytics is hiring. So if you're interested, if you are a data scientist, do contact me. We are very keen to hear from you. So that's all from me. And is there any questions?